Okay, let's work some more free fall here. These are free fall practice 2. And so for these problems, we're going to toss something up in the air. So throw an object, a ball, up. Right? That's it. Straight up, since we're still talking about motion in one dimension. So let's analyze the motion of something that has been tossed straight up in the air. All right. A coordinate system is required. So let's make a coordinate system. And usually the origin of the coordinate system is the initial position of the object. It doesn't have to be. But certain problems are easier to work out if you make the origin of the coordinate system coincide with the initial position of the object. So, and like I said, we don't have to worry about left and right, but I'm just still going to draw both these axes. All right. And next I need to say, okay, so which way is positive? I'm going to make up positive. But if up is positive, remember, all objects in free fall accelerate downward the entire time they're in free fall. Their acceleration points down, and that's very confusing because objects don't have to be moving down to be accelerating down. Yeah. And so that means, if up is positive, definitely down is negative. And if down is negative, that means that the free fall acceleration in this problem has to be made negative. So again, the acceleration here, it's still little g. But with this coordinate system, that has a value of minus 10 meters per second squared. All right. And so now let's do a problem, all right? So let's say that we toss this thing up in the air. With some velocity v naught. And it goes up and then returns and it reaches back to its initial position after a total time of 4 seconds. All right. That's the time to return to its initial position from when you threw it. So that is the total time in the air until it comes back to your hand. It's 4 seconds, yeah. All right. So let's write some things down now. Let's make a list of other quantities that we know and then what it is we're looking for. So t is equal to 4 seconds. I know that the acceleration is minus 10 meters per second squared. I don't know v naught. That's probably one of the things I'm going to be asking about. What about its displacement, delta y? Do I know that? Yes, you do know delta y. Delta y, remember, that is its final position minus its initial position. So it started off at 0, where your hand is. It ended up at 0, where your hand is. So its displacement is, guess what? It's 0. It didn't go anywhere. It did go up and down, but that's equivalent to not going anywhere. Its displacement is 0. The distance that it traveled is not 0, right? Because it went up some number of meters and came down some number of meters. The total distance, you add those two together. But its displacement has a very specific meaning. It's the difference in position between where it stops and where it starts. And so in this problem, it's 0 meters, so yay. Now, let's look for V naught. What is this value right here? How fast did we throw it? So that it lands exactly 4 seconds later. And there are several ways of getting the answer to this question. Okay, several different ways of getting the answer. There are some intuitive ways of getting the answer if you understand what acceleration is. Okay, so think about it. First of all, with projectile motion problems like this, there's a really nice symmetry to this problem with respect to time. However long it takes getting up to its highest position, that's the same time it takes to get back down to where it started. So if the total time in the air, and this is only if you catch it at the same level where you threw it, but if the total time is 4 seconds, guess what? That means that the time it takes just to go up is 2 seconds, all right? And so then the next thing to think about is, this thing is slowing down 10 meters per second every second, right? So if it starts off with some velocity, all right, positive velocity, and it decreases 10 meters per second every second, how long is it going to take to stop at its highest position? Because when it gets up here, its velocity is 0. It's got to be 0. Right? It's slowing down the entire time it's moving upward. At some point, it stops and it turns around and comes back down. So how fast does it need to be moving so it takes 2 seconds to stop if it's losing 10 meters a second every second? Some of you said, oh, it's easy. It's got to be moving 20 meters per second. Okay. Yes, indeed. But you know what? Let's use the equations we have. All right. And again, at this point, there are several different equations you could use to figure out this V naught. So let's do that. I'm going to use, the equation I'm going to use is let's use delta y is V naught times t plus 1/2 a t squared. Now, the delta y, remember, the total delta y is 0. Now it's algebra time, right? Because we want to solve for V naught. So algebraically, we want to get this V naught t term by itself, so subtract 1/2 at squared from both sides. When I do that, that cancels the 1/2 at squared that's on the right side of the equation. Next, notice here, this is t squared, and this is t. That means you can divide both sides by t, all right? And then on the right side, I'll have V naught, right? Because t over t is 1. And then t squared divided by t is just t. So now I have minus 1/2 a times t is equal to V naught. So we are almost there. So now let's go ahead and put in the numbers. Remember, for this problem, a is minus 10. And the time was 4 seconds. Okay. So a minus times a minus is positive, so the minus signs cancel out. So the math part of this is 1/2 times 10 times 4. So 1/2 of 10 is 5, and 5 times 4 is 20. And then we have seconds here that cancels one of these guys. And so we're left with meters over seconds, which is good. So there's your V naught, 20 meters per second. All right. And then finally, another way we could have done this problem is by the following. Okay. So V naught, total time in the air is 4 seconds. Which means the time to get up here to the top is 2 seconds. And again here, the speed of this, its velocity at the very highest position is 0. So at this position, I know that V, and you can actually call this V final. I know it hasn't stopped moving entirely yet, but you could, if I'm looking at just the part where it goes up in the air, it takes 2 seconds to get up here, and its velocity at this position is 0. All right. So then now let's try using, let's try this one. How about V naught is equal to, take that back. It's V final is equal to V naught plus AT. Yep, that's one of the 4 equations we're going to use here. And V final up at the very top there, that's 0. And since we're solving for V naught algebra, subtract AT from both sides. Now we can plug in the numbers. So this is minus, the value of A is minus 10 meters per second squared. And the time it takes to get up there is 2 seconds. Okay, so numbers, let's see here. Minus times a minus, that's positive. So 10 times 2 is 20. And this seconds here cancels one of those guys. So again, 20 meters per second. That's how fast it had to have been tossed up in the air to be in the air for 4 seconds. 4 seconds is a lot longer than you might think it is. We should have a contest to see who can toss a ball up in the air and have it stay up for the longest times. Ball toss. If anybody's watching this video, ball toss contest. If somebody reminds me about this on Monday, we can actually do this on Monday. All right. So that's the end of this little review session. Thank you very much.